Hey guys, welcome back to another episode of Introduction to Computer Networks. This is Polly streaming live from NTU. Yeah, how are my students? Hey, hi, Shu Chen, Aslam, Yong Yi, Ryan, hi, and Yuji, Amy, and Hong Ming, Yu Jie, Cheng En, Zhixiang, Jia Xuan, Bo Yao, and Nico, and Matthew. Okay, good. Good to see you guys popping in. You know what? Let's check out the announcements today. So number 3 is always about the assignments, right, this week. So we have PA3 due. Quiz 11, 12, and 13, all due by Saturday, 6 p.m. Okay, so you guys have been doing very well about these assignments. Keep them going, right? Oh, Yanjia, Yuting, Zixuan, and Zhuxun. Hey, good afternoon, guys. And number 4, haha, exam 1, guys. So yeah, the nice old days are gone. Starting next week, the first exam is coming up. So the class will get a little bit more intensive. So next Wednesday, hey guys, those who have paid attention to the announcements in the Exam 1 channel will see that next Wednesday, during the entire exam, you will need to fill a Google form. Yeah, so on the form, there are all these exam questions. In the meantime, you also need to join a Google Meet session where the camera needs to be on and facing, so you need to take your headshot from shoulder up. Okay, so you do need to find a place that has stable internet connectivity, and to make sure also that your laptop or smartphone, whichever you choose to use, the equipment is also stable. Okay, and you are placing your equipment, your camera, at the right angle. So for that purpose, we're going to do a test run for you to set up the exam environment. Okay, so that will be 10 minutes after the lecture tomorrow. So that's after Polly closes the stream. Then you would join the Google Meet session and make sure that your camera is placed at the right angle and the internet connectivity is stable. So we'll tune in and Polly will know, hey, you know what, you're okay. Okay, so with that done, it's one less thing to worry about for the exam. So the rest of the time, the rest of the week, all you need to do is just to focus on preparing for the exam. Okay, good. So that's all the announcements. The topics today. Okay, so topics today remain somewhat light. Okay, so 3 sets. First is to wrap up. Hi, Lucas, Ming Huang, and Ali. So first is to wrap up HTTP, the protocol itself. The 2 other topics are cookie and cache. These are the add-ons to try to improve the web service. Okay, so we'll talk about those later today. First thing first. Last week we started talking about the messages generated by HTTP protocols, particularly the HTTP request, that is the message generated typically from the client to request for web objects from the server. So you see there that there's an example. You learn the general format of a HTTP request. You see also a number of these methods a client can use to interact with the server. Today, let's talk about the response message, the message generated from the server and sent to the client. So in this video, it's a little bit long, a little bit more than 6 minutes, but you will see an example, a full example of a response message. You see also a general format. The first line is a status line, a special line, and then followed by a number of these header lines, just like the request message. An empty line, just like the request message, but very different from the request message. In request message, there's no payload, no data part, but in response message, we have the data part. And this is typically the part containing the web page a client asks the server for, right? So 6 and about 20 seconds. Now, finally, the HTTP response message. Okay, the second type of messages in defining the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component in the status line. Second, this is the status code. Okay. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Okay. Some more related to the server, some more related to the object being requested. Okay. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates okay, meaning the HTTP server is working well and the object you're looking for has been found. And it's going to come here in the body entity. Now, second part, the header lines. We see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Apache is one of the most commonly used web server implementation. Yeah, I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I say that it's actually rising. Okay. So I think maybe in just a couple months, there will be more Nginx server than Apache servers. Last modified. Yeah, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's a really long time ago. All right, ep8. What is this? This is actually ep8. For each version, okay, of the object that you are downloading, there comes also with a version number. So ep8 there is to indicate the version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading. If there are multiple users there using different web browsers trying to upload the file, for example, poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break time, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. Okay. So server there can actually tell the client, you know what? I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send the request more officially instead of using the head command, using the real get command and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, the size is a bit messy. Let me clear the markups. Keep alive. Oh, good.
this web server implements persistent connection, okay? And so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right. So if it's more than 100, then you will force close. The server will force close the connection. So connection, keep alive. Content type. Yeah, just like the client size header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file, and it's coded in ISO aa59. Right? And empty line, indicating this is the end of the header lines. Right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages.
All right, so the second video, brief, slightly more than a minute, it's just to show you the variety of status line the first line in a response messages could be like. So that includes the 200 OK status line and the very well-known 404 not found status line.
Next is just to share a bit more. HTTP response messages status code. We've seen earlier in the example 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means your HTTP request format is not quite correct. Bad request. 404, that means the object you are asking for is not found. 505, HTTP version not supported. So in case you're using a very, very, very old browser, or if you're contacting a server that's very, very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 505.
All right, so those are the status lines. And we are in quiz 11. So as you can see, it's actually similar to quiz 10, where we are testing you guys' knowledge of HTTP requests. And this time, this time we will be tested the HTTP reply message format. So this is again a result of a sniffer, okay? And this is the HTTP response message that's sniffed. So based on the content, Q1 of quiz 11 asks, was this web object found successfully? How do you tell? Okay. Second, how many bytes are there in this web object? How do you tell? And quiz Q3, what are the first 5 characters of the web objects that is returned by the response? So this is the first 5 characters of the web object, not the first 5 characters of the reply message. Okay. So by the way, reply messages, I meant response message. Good. Now let's go to the scored. Channel W5, quiz 11. So guys, this quiz is straightforward. You have 3 minutes to work on it and 1 minute to type your solution. And Polly is looking for fast and correct response for bonus. Ooh, okay, we have already a response already, but it's okay. Take your time. It's better that you try to address the quiz yourself so that you can double check whether what you heard you understand what you heard correctly. So let's go. All right, as you can see, right, very straightforward because we see 200, okay, that means the request was successful, okay. And we see from the content length. So let me see where content length is. Yeah, content length 4 bytes. So Yuting, very good. And the first 5 character, yeah, of course, the first 5 characters following the empty line. Very good. So straightforward. Now let's come back to the lecture. So next topic, it's called demo. It is just to show you that how one can interact with the real web server. Okay. So the first video, forgot to greet. Okay, hi Hanjun. First video is to talk about the demo setup.
So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're going to use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80 where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So Telnet is a remote logging application, just like SSH or RSH, if you know what it is. It's another remote logging command for native Unix users. All right, so Telnet is very, very old. Many operating systems probably doesn't support it anymore, but I've already installed it on my Mac, so we're going to show that in a little bit. Now, once we Telnet to the web server, and we'll type up some things. Okay, let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the Telnet here is a HTTP 1.1 client, and host gaia.cs.umass.edu. Right, so header line. So essentially, we are trying to do a human web browser, okay, by typing online right here an HTTP request message. So once we are done with this, we hit return, okay, and then we hit return again. Needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the Telnet program. All right, so let's switch to the demo mode.
Okay, so here's the real demo. By the way, Telnet is a remote logging utility, just like SSH, except that it's not secure.
All right. Telnet to gaia.cs.umass.edu at port 80. All right, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh wow, that's pretty long. The path and file, pretty long. Let's copy it from the sides. And over here and print. All right. And then host poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long in fact. But it looks like it's an HTML file, right? It's an HTML file. This is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here. Okay, and we also say we are host poly.ntu.edu.tw and an empty line and then return again. the whole message gets out to the web server at gaia.cs.umass.edu, and the web server returns this http/11 to 200, okay. And header lines, number 1, the date. Header line number 2, the server. Oh, it's an Apache server. And X power by PHP, I see. Content length, content types. And hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see, interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online as a web browser. All right. Good. And I think let me just go back a little bit here. You see here, 200 is a very classic example of, hey, the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics, and syntax of HTTP.
All right, good. So we're done with HTTP. Now, cookie and cache, these are the two add-on protocols. First, cookie. So this has something to do with something we mentioned in introducing HTTP. It's a what? It's a stateless protocol. What that means is the server does not store anything about the client, okay? Memoryless. So we say that this makes the server implementation simple and efficient. But that might not be the best thing we do, depending on what the web services are for. So if you guys have experienced shopping online, okay, it would be really tedious if you select an item to purchase and you have to finish the transaction before you purchase another one. It would be really nice if you can just click and select the products, put them in the basket first, and finish the purchasing at once. Okay, so that is something that you cannot quite do with the stateless HTTP. So cookie is created for convenience for returning users. Okay, so in this video you will see the basic mechanism, and following that, a illustrative example.
Next, cookies. Yeah, many websites these days will try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate a corresponding message if you click OK to insert cookie. And that message is going to carry, again, a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, OK, I will allow setting up the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay? So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, that arriving at the server, the site will then create a unique ID Okay, and that will be an entry being added to the backend database. Right? So that ID is going to be carried. Okay, in the message, the site sends back to Susan. So that's going to be set cookie and then the number created here. All right. So local hard disk you have there, or Susan has there, will have that entry, okay, set up in the cookie file. So this will go back to the server, okay, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, okay, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Okay. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry carrying unique ID ep8. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website, Amazon.com, the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. Okay, so in your initial HTTP request message, there's not going to be any cookie special header lines. All right. So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID, okay, for this particular user, okay, and add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. Okay? And hey, see the ID created is carried over through the HTTP response message back to the user. So web browser here sets up one extra entry saying, hey, for Amazon, the website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am user 167A header line. Right? So here the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So response message. But the response message might also contain additional content. Okay, server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item, okay, and then recommend potentially items you'll be interested. Okay, so that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you're looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, okay, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, on your cookie file, for all the subsequent HTTP requests, it's going to by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there.
All right, so now you hear a little bit that cookie is not always perfect. Okay, so in terms of usage, it brings convenience, but in terms of usage, there's also a downside of it. Okay, privacy concern. So in this next video, you will hear privacy concern on the usage side, and there's also a technical drawback maintaining all these cookies.
Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, the cookies from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that. Right? So convenience. But on the downside, those websites would be able to learn a lot about you. Okay? So you store emails, that's pretty much your personal life. You store your purchases there, that's pretty much also your personal life. Okay? So over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell lot about you. That's why people are freaked out so much about these big sites, okay? Allowing them to set up cookies, allowing them to store information about you, okay? So downside, privacy. Okay. Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay? No storage requirement. And you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here, you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed in the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? Then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states.
All right, so cookies, good and bad. So use them cleverly, all right? Next add-on, it's called caching. So in this video, you will hear Polly explaining what caching means and how the local cache, this is the first form, the simpler form of caching, how local cache works.
The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay? So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay? So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay? Because as a result, we don't need to send the object, and that reduces the delay. And we also reduce the bandwidth requirement. Okay? And so saving the bandwidth is going to be good for everybody. So the way it works is this. Okay? So the first time the client downloads a web page, it's going to keep a copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modify since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cache copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modified since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T.
All right, so you see in local cache with the mechanism, you save some bandwidth, but you don't necessarily save much time. Okay, now the next, web cache. As you heard in local cache, so what we do is to save the web objects that are repeatedly requested on the local, the client's hard drive. Okay, so web cache is this, to store web objects repeatedly requested by a group of clients, okay, somewhere close to the clients. And that somewhere is a special server we call the web proxy server. So in this video, you will hear the web cache mechanism.
Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. The main difference is this. In local caching, we keep a copy of the object here. Okay? But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay? And in conditional GET, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay? Sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the object somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay. So object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client of the original server. Web cache there, request object from the original server like a client. Okay. And after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it served the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? a web cache like that is actually preferred by the ISPs, okay, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. Okay? So a lot of times ISPs might encourage you to set a web cache, okay, on your browser. Now, let's go through a few examples to detail, okay, why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
All right, so in the next 3 videos, you see the 3 versions of the example. So the first one is the basic setup. So after Polly introduced the setup, you will see Polly calculating the response time requesting objects in that setup.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, okay, coming down this way. Right? And that is 1.5 megabits per second. Now, let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set at to 2 seconds. And the link, access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hub, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right? So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay, now this is very low because utilization is super low. So let's say microseconds, right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second scenario.
Yeah, so the second scenario is to what? Expand the bottleneck bandwidth. Okay, so
in scenario 2, let's try to address the issue here, because this is the bottleneck link where the delay came from mostly. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why a millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between two routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds, which of these three components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now, in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link.
All right, so hey, expanding the bottleneck link, yes, response time dropped, but it's very costly. So you will see in the next video, which we don't have time to play. So that is something that we'll play tomorrow morning, the first thing. So yeah, in the third scenario, you will see that using the proxy server not only reduce the response time, not only reduce the traffic, it's also very cheap. Okay, so it's got the benefit of reducing response time and reducing traffic, but also affordable. Okay, so that is something that we'll talk about tomorrow. With that said, I say goodbye. That's all the time we have. Okay, good. ending the stream now.